Bismillahirrahmanirrahim. This is our first lecture on passive electrical filters. In this lecture, we will discuss the structure of passive filters, and then we will categorize them into low pass filter, LPF, high pass filter, HPF, and band pass filter. We will also discuss the first order as well as second order filters based on the number of capacitors or inductors that we are using in our filter circuitry. So these are the contents of our today's lecture. We will study the electrical filters, and after that we will go deep into the design of these electrical filters. We'll study passive filters, and then in passive filter we will study low pass filter, high pass filter, band pass filter, and band stop filter. We will discuss the first order low pass high pass filters, its frequency response, its cutoff frequency and central frequency FC. And after that we will also discuss the second order filters and the usage of such filters in pulse shaping and some scenarios. We will also study the formulas with the help of some examples for better understanding. So most electrical filters are circuits that passes some bands of frequencies and rejects the unwanted bands. So as you can see in this figure, we are having a composite signal that is the combination of a low frequency, high magnitude signal and some high frequencies. So these are three frequencies which are being combined to form this composite signal. If we give it to a low pass filter, only the lower frequency will be allowed to pass. If we give it to a high pass filter, so this higher frequency will be allowed to pass through this filter. If we allow the band to pass, then only the intermediate frequency, which is right here, this frequency will be passed, and the rest of the frequencies will be signals of such frequencies would be rejected. So this is the signal in term of, let's say, x of t, whereas this is the response of the signal in term of frequency. So this is x of f. We check the amount of signal, the magnitude of the signal, either voltage or current, at this output with respect to frequency. So if the frequency is lower, so we will be having a low pass filter. If frequency is higher, we would have a high pass filter. And if we have a range of frequencies that are being rejected and some are passed, so those filters would be known as the band pass filter. Whereas notch filter, it is just like the cut that we make in the clothes, just like this, that we flip it and then we cut it, so it becomes something like this. So notch is this thing, but actually a band pass filter might be, a band rejection filter might be like this. If we say that this is an ideal, so it will be like this. If we use capacitors of some higher values, then it would be something like this. We will discuss these things later, but this is just for general understanding. The frequency at which the transition between passing and rejection occurs is termed as the cutoff frequencies. Cutoff frequencies are those frequencies at which the change in this graph occurs. So this is the cutoff frequency right here. This is the cutoff frequency right here. We are having two cutoff frequencies here and here, and we are again having two cutoff frequencies. So two cutoff frequencies means that we are having two capacitors or 2 inductor or 1 capacitor, 1 inductor. 1 FC means that we are having 1 capacitor, 1 inductor. So and of course some resistor for voltage drops. So 2 cutoff frequencies, 2 components, 1 cutoff frequency, 1 component. The band of frequency that is pass are known as the pass band. So pass band is what we will get on the output. The frequencies that are rejected are known as the rejected bands. Filters can be active filter or passive filter depending upon the component that we use. If we use capacitor, inductor, resistor, inductor L, this would be a passive filter because all can only do drops, nothing can give us extra energy. So passive filter would have these things. Active filters might have some amplifier or it can have, let's say, some circuitry for gain, let's say BJT, etc. or FET. So when active components are in the circuit, we call it the active filter, and when passive components are in the circuit, we call it passive filters. Now let's check the general design of such filter. We have already discussed it, but let's summarize it. The simplest filters are constructed by 2 passive elements, say RC or RL. So the capacitors that are constructed using RC are lighter in terms of weight. These are a bit bulky. That's why when we design an active filter, we use RC as well, because capacitors are lighter and semiconductor devices are also lighter, so it becomes a light filter. When we want some high fidelity voices or something like that, then we go to this RL filter. So inductors are bulky and we have bigger devices for it. We also use higher values of resistances in it because the inductor requires that. So this is about the general structure of the filter. The filter that passes low frequency are referred as low pass filter, and those that passes high frequency are known as high pass filter. These are some of the structures which are for ideal filter. So the pass band is to the 0 side, so it is a low pass filter. The pass band is to the upper side of the band, so it is a high pass. The pass band is in the between lower and higher, so it is a band pass. And there are 2 pass bands, this one and this one, so this is a band stop filter. It is stopping this particular band. So say we are having some talking in a phone line, and let's say this is our talking region, but there is a bit constant noise, say a tone in our communication. Let's say we are talking and there is some background tone of 115 hertz in it. So this is a heavy basic tone. What will we do to remove this tone? Of course, we will use a band stop filter that will notch out this particular region. So what will be the structure of that filter? That filter would be having something like this. So if we remove this thing, our voice band would be something like this, and now it is not having this 115 basic voice. If we remove 3-4 components from our voice, the quality of our voice won't affect. But if we accept this 115 hertz noise in it, then it can be a bit noisy to our ears. So notch filters are used in such scenarios. Now coming towards the passive filters. passive filters are made up of capacitors, inductors and resistors and have no amplifying elements. So this is the basic definition of a passive filter, that it will have no amplifying element and will consist of these three components R, L and C. So it means that the output can never be greater than the input. So output, the gain in voltage or current can be lesser or equal to 1. Again, we are having three types in passive filters: the low pass, band pass and high pass filter. Also, the filters are named based on the range of frequency. So higher frequency would be termed as high pass, lower frequency filter would be termed as low pass filter. So that is another definition. The rejected band is actually attenuation in the signal. So if we have, let's say, two sine waves, one is 13 sine of 3t and other is 15 sine of 30t, and we want to reject this particular frequency from the pass band. So what will we do? We will reduce this magnitude of this signal. So if it is like 1 sine of 3t plus 15 sine of 30t, so this 15 is much greater than this 1 as compared to this 13. So this is what we do by saying blocking the signal. Passive filter never gives a positive gain, as this equation says that the log of 1 is 0 and the log of anything lesser than 1 would be lesser than 0, so it will be negative. Minus 1, minus 2, minus 3, minus dBs would be the negative if we multiply 20 with it. So this thing that it never gives positive gain, it always gives negative gain because the gain is either 1 or less than 1, and the log of less than 1s are negative. Input signal is usually alternating voltage with a band of frequencies, as we discussed in this particular example, that we had this frequency 3, omega equal to 3 and omega equal to 30. So a band, a range of frequency is given at the input and the unwanted signal is attenuated. Depending upon which way around we connect the resistor and capacitor, we can get low pass and high pass filter. So no matter what components we have, if we connect it in the right manner, we will get the desired filter. But if we connect it in the manner that is not wanted, then we will get a wrong filter. So R and C are the components that we will use in our filters from now onwards. But if we connect R, C in even series and take output from this port, it will behave like something else, and if we take output from this port, it will behave like something else. So this is an important point, that the order, the sequence and the structure of the components that we connect is important. Now coming towards the low pass filter. Low pass filter allow low frequencies. So this is the first definition of the low pass frequency. So it allows low frequencies and starting from 0 Hertz. So it is always included in the low pass, that it will always allow a DC component to pass through it. So 0 Hertz is DC component, and we can pass DC component by just using a capacitor. How? If we use a capacitor, the AC components will be grounded and the DC will be passed on. So this gives us a notion about the structure of the filter. The cutoff frequency is determined by the use of this capacitor and some resistor with it. So at this point we have decided the structure of the filter, that it must have a signal parallel to ground capacitor, and a series resistance with it, so that we can calculate the Xc is equal to R equations omega. Okay, so this is the first thing that we should keep in mind. A simple passive LPF can be easily made by connecting together in series a single resistance with a single capacitor, as we discussed here and as this figure suggests. In this type of filter arrangement, the input signal Vin is applied to the series combination of this and this capacitor and inductor, but the voltage is always taken from the capacitor. So as we speak, the capacitor is used as the terminals to be connected to the output side. So the output will not have high frequencies. If we have some high frequency, what will happen? Capacitor Xc is 1 over j omega c. So if omega is high, Xc will become lower. And if Xc is low, what will happen? The signal will just go through this side and will be grounded. So lower Xc is not good for high frequency signal. So high frequency will be attenuated here. A component will be passed here, but it will be a very lower component. Whereas if we say that omega is low, let's say omega is 0, what will happen? Xc will be infinite. So this will be an open circuit for a low frequency. So lower frequency signal would go directly to the V out. So this is the case for the for such a filter. This type of filter uses one capacitor. So what is meant by this? This means that it is a first order filter. It will have one derivative or one integration in its equation. So a first order filter is also known as one pole filter. So it is a one pole filter, and because it has only one reactive component, say a capacitor is connected in this circuit, at low frequencies the Xc reactance is large. So this thing Xc is large at low frequencies. This is a pretty much better pen. I haven't used this before. I guess this is very visible. Okay, so the Xc is higher at low frequencies and lower at higher frequency. Let me do some amendments with it. I guess some of the part is hidden over here. Okay. Now it's better. So at higher frequency, what will happen? This Xc would be grounded and the signal will be grounded as well. Okay, so this is it for the low pass frequencies. Now digging in more into this first order low pass filter, as we know that this is a series circuit. So in a series circuit we use the divider rule for voltage signal. We discussed yesterday that most of the signals are voltage signals, because a lower voltage can easily be amplified by some other circuitry. So we use voltage as our signals. Also the resistance combination divider rule is applied in it, but since the R2 in here is actually the Xc, so we will say that it is R2 divided by R1 plus R2 into N, that will be converted to xc divided by r plus xc into Vn. So this is the format of our equation. This is general format. In this we are using the complex values of xc, r and this thing. If we want to find the magnitude of the output signal, only the magnitude of the output, then we will combine these things and we will use the value without j with this xc. So that will become xc divided by this thing. So this is actually the z. So z is equal to r plus xc in its complex values, or z is equal to r square plus xc square in its magnitude. So this is only the magnitude of that phasor, and z is again this thing. This is replaced in this equation. So we can write this equation as V out is equal to V in xc divided by z. Z is the total path resistance. So R xc. Okay. Now what is xc? Xc is the impedance of the capacitor in terms of ohm. So xc is 1 over omega c, and omega is 2 pi f. So omega is replaced as 2 pi f and c is written, and this gives us our xc. So now we have all the values for our equation, so we can find the V out at any frequency. Say we are having a range of frequencies from 1 Hz to 100 to 1000 to 10,000. We put this in this equation, and then in this equation, and then we put this and this and this as our f. We calculate xc for 100, 1000 and 10,000. So we calculate xc, and then we put this xc in this equation, and we find this voltage. So if we draw this equation, it will be something like this. This thing will be decreasing. Why? Because at higher frequencies the voltage will be attenuated. So this will give us our physical filter structure in terms of frequency axis and the magnitude of signal as V out. Okay, there is an example on this low pass filter. The low pass filter circuit consists of a 47k ohm resistance. Sorry, this thing is a bit wrong, let me correct it. So this is a 47 k ohm in series with a 47 nanofarad capacitor, which are connected across a 10 volt sinusoid supply. So this is a 10 volt supply, and calculate the output voltage at frequency 100 and again at frequency 10,000, and this thing, this is OR. Okay, so this is our example that we have to calculate the output at 110k hertz of frequency. So for that we will calculate the XC100 and XC10k. So how did we calculate that? For that, let's check first that what is this output. This output is the component of this input. We can calculate this output by dividing this XC divided by R plus XC and then multiplying by Vn. So this is our V out. Now this is in phasor in magnitude form, so square as well. Okay, now calculate XC 100. So for that we will use XC is equal to 1 over 2 pi f c, and f is 100 here C is how much? C is 47 nano. So if you put these values in it, 47 nano multiply by 100 multiply by 2 pi and whole inverse 1 hour, and we get this 33.8 K ohm. So this is our XC. Now we can calculate our V out. So V out would be 10 volts multiplied by XC divided by resistance square and XC square. So resistance is 47K. So it is not 47K. This is 4.7K as we see in here. I was thinking that how can this thing be wrong. Okay, so this is 4.7K, and this nomenclature was, I guess, used in the lab as well, that 4K7 ohm, 4K7 ohm. So this was 4.7K ohm is written in here. Okay, so we can also write it like this. So 3700 ohm would be written as 3K7 ohm. Okay, this was a general information just because we had some doubts in it. Okay, so we put this for 700 square and 33863 square, and we got 9.9 volts. So the input voltage is 10 and the output voltage is 9.9 volt, which is almost equal to 10. If we want to calculate the gain in terms of voltage, what will we do? We will write 20 log output by input, 9.9 divided by 10. So this turns out to be 20 log of 0.99, which is almost equal to 0. So say minus 0.9. Yes, so this is like, I don't know what will be the value of it, but this log will be negative dBs. It will be less than 0. So minus 99 or minus 0.1 or something else. Just calculate it. Okay, now we repeat the same process for XC equal to 10K. So at 10K we first put 10K as frequency and 47 nano. Nano is 10 power minus 9 if you don't know. So we put this thing in it and we found 33.6 as our XC. If we calculate the output now, output would be 10 multiplied by 338 divided by 338 square plus same resistance square. So this gives us an output of 0.7. So first it was 9 and now it is 0.7. It is even lesser than 1. So the gain would be 20 log 0.7 divided by 10, which is 20 log of 0.07. So here it was 0.9 and it was 0.0. So this is very much lower in negative values of dBs. So this is what happens if we increase the frequency. So this clearly says that the SAD filter, this filter that we are discussing, is a low pass filter. It allowed 100 Hz, but it didn't allow 10K Hz. The frequency response of this low pass filter is a bit easy now. It will be studied with the data from the previous example. So we can see from the result that the frequency when it was 100 Hz, the response was good, but when it becomes 10K, the response was bad. So that means that it was a low pass filter. The band that was passed was in in that example is here. By plotting the network's output voltage against different values of input frequency, the frequency response curves or body can be found, which is shown like this. We can also find the phase of this same filter. What is phase? Phase is the angle which is being observed by the output when it goes through the circuit. So first the circuit was resistive because the capacitor was not acting. The circuit was resistive because all the voltage was forwarded through the resistor from input to the output. So this will show us a zero angle, which is shown in here. As the frequency increases, the capacitor starts its working and the circuit becomes capacitive at higher frequency. So all the voltage is being grounded, and capacitor is 1 over j omega c. So this will give us a minus 90 degree with the output voltage. So when we increase the frequency, the voltage angle, if we check the voltage in here, it will have a minus 90 degree angle with it. So after the cutoff frequency, we see that the circuit is having a phase shift of 90 degrees. So this happens at very high frequency. At lower frequency we get 45 degrees and greater than 45 degree, but not this 90 degree. 90 degree is at infinity, theoretically. What is this cutoff frequency? Cutoff frequency is the knee of the graph at which the circuit starts attenuating its output, and it gives output of 70% of the input. So 70.7% of the output is at 45 degree. So this condition is known as the cutoff frequency voltage. 45 degree is actually the halfway between 0 degree and 90 degree. So we can also call it the half power bandwidth. So half power bandwidth is observed at cutoff frequency. So cutoff frequency हम किस तरह define करेंगे? Xc is equal to R and 1 over 2 pi Fc is equal to R. Now separate this F. 1 over 2 pi Cr is equal to F. So this is our cutoff frequency. For the same circuit that we discussed, the cutoff frequency is at 720 Hertz. How we calculated that? We had 4K7 ohm resistance and 47 nano capacitance, and we put that in this equation for Fc, and we got 720. So at 720 we will get a 45 degree phase, and we will have half the voltage of 70.7%. So 70.7% is actually 1 over under root 2, and 1 over under root 2 in logarithmic scale is the 3 dB. So 3 dB bandwidth, half power bandwidth, or 1 over under root 2, which is 1 over 707. So this 0.707, you might be familiar with it. So this is what happens if we increase the frequency, that the change in phase as well as voltage occurs. Check this thing by yourself, that what is cutoff frequency, what is half power bandwidth, and why we use 45 degree as our half power. Okay, now going towards some higher order low pass filter. Second order filter will be a cascaded version of the series version of the low pass discussed filter. This is similar structure, but we are combining two circuits. This is first stage This is first stage filter and this is second stage filter. So we will get double attenuation due to this. So if we had a 20 dB per decade loss by the previous filter, now we will have 40 dB per decade loss in the signal after cutoff frequency. So this is termed by this equation, that number of series filters multiplied by 20 dB will be our combined loss or gain. Okay, so there is more than one RC network, that's why it is known as the nth order for such case, and n is equal to 2, so this gives us a second order low pass filter. Also we can calculate its corner frequency or the cutoff frequency as 1 over 2 pi r1 c1 r2 c2. So this equation is now modified. We are multiplying the capacitances and resistances for 2 times because we had 2 circuits now. Also the second order low pass filter 3 dB frequency, which is that 3 dB gain which we discussed, can be found by Fc 1 over 2 power 1 over 2 minus 1. So these are the equations that you should probably be remembering by yourself. Okay, and passive low pass filter gain is 1 over under root. So for the first filter it was 1 over 2, but now it is whole n. N is 2 here because these are 2 filters. It can be 2, 3, 4, 5 for nth order. So this is the low pass second order filter. Let's discuss its graph. The first filter which we had previously had this 3 dB graph, and the second one is also having a 3 dB graph, but the loss is now 20 dB per decade converted to 40 dB per decade. So first filter had this knee here, the second will be having the knee here. So this is our FC for the second, this is the FC for the second. Here are some of the things increased. So if these things are increased, this will lower this frequency, bigger denominator, lower FC. So first we had 1 over 2 pi 2 pi RC. So 2 pi RC was bigger than 2 pi R1 C1 R2 C2. So that's why the first one is here and the second one is here. So this is a bit lower FC2 for the second. Okay. And the gain is converted to minus 40 dB because the graph is now more steeper. It is not like this, it is like this. So this is the frequency response of second order filter. We use filters in pulse shaping. If we have such inputs, let's say a very steep increase in the voltage, and we pass it through a resistor, what will happen? This resistor will make it a bit linear, and if we pass it through a capacitor, what will happen? It will integrate these things. It will start from here and will add up all the voltages up to here. So integrator can be formed by a simple low pass filter as it decreases the high frequencies. So high frequencies are decreased and lower frequencies are remained, which make this thing a sawtooth wave. Not a sawtooth wave, but a triangular wave. So this is a triangular wave now. So this is a phenomena which can be observed by taking a square wave at the input and using a low pass filter. What will we get? We will get this way. The high pass filters. High pass filters allow high frequency and do not allow the low frequency. So as the name suggests, this high pass filter will work totally opposite to the one that we discussed. So this is the structure of the high pass filter. At high frequency the capacitor becomes short, and at low frequency it becomes open and do not allow the signal to pass. So if we have, let's say, a frequency band, at low frequency it will not allow the voltage, and at higher frequency it will start allowing the voltage till f equal to infinity. And then we take the output across resistance. So as we spoke earlier, that we had same structure, but we took output from this side and gave input to this structure, and now we are taking output from this thing, so that makes it a high pass filter now. So in this circuit arrangement, the reactance of the capacitor is very high at low frequency. Xc is higher at low frequency, turning out that it will not allow the input signal through this capacitance, because let's say if we are having a DC signal, so capacitor is open for DC, so it will not allow. After the cutoff frequency is reached, after this Fc is reached, what will happen? The circuit will allow some of the voltage to pass through it, and after increasing the frequency more, we will have all the voltage available across this thing, because this resistance would be higher as compared to the drop associated with it. Okay, so this is the high pass filter. First order high pass filter is having same frequency equation as the low pass filter, but only the difference is that its structure is different. Its structure is that we take the output from the resistance instead of capacitor. The Fc is 1 over 2 pi Rc, and the phase is tangent inverse R y divided by x of this total z. Okay, but this is the phase, so this is calculated from the omega's equation. Okay, so now if we want to calculate the output of this circuit, so V out would be Vin and multiply by same voltage divider rule, but here we are having R divided by R plus Xc now. So square under the root will give us R by Z. So R by Z is giving us the voltage gain. The voltage gain will always be lesser than 1 because we are having R plus X greater than R always. So this is the typical high pass filter. If we examine the curve of this response, so we will have a 20 dB per decade increase till we reach this 3 dB 45 degree minus 3 dB 45 degree point, and after that we will be having our pass band. So pass band is for higher frequency. At low frequency the capacitor is working, and at higher frequency the capacitor is short, it is not working. So if we graph its equation, it will be something like this: Xc divided by this thing. In previous equation we had Xc above, so due to that we had minus 90 degree, as Xc is 1 over j omega c. Now the Xc is in the downside, so 1 over j omega c will make this thing j to go up. Are you getting my point? In the first equation we had Xc divided by R plus Xc. So we had this 1 over j omega c that was making a minus 90 degree angle. Now we are having R divided by R plus 1 over j omega c. If we make this thing go up, let's say this R is not here, what will happen? This will be j omega c. So j is 90 degree plus. So this will start from 90 degree, and at higher frequency this will become 0. So this is the only difference, that we had the phase of 0 to minus 90 in the previous, and plus 90 to 0 in this one. So again, C always causes a 90 degree phase shift, but depending upon the voltage divider circuitry, that where are we taking the voltage? It can be from minus 90 to 0, from 0 to minus 90, or from 90 to 0. So this is what happens for capacitors and inductors. Let's study an example on this FC. Calculate the cutoff breakpoint frequency. So cutoff frequency is also known as breakpoint frequency. Remember this thing. Okay. For a simple passive high pass filter. Passive means that there will be no positive gain. High pass means that we will take output from the resistance, and it will be like this. Okay. Considering that an 82 picofarad capacitance is introduced in the series with a 240k ohm. So this is 240k, this is this thing. So FC would be equal to 1 over 2 pi RC. So put these values in it and we will get what? 8k hertz. So if we draw this thing and this is our 8k, so what will happen? This will be something like this. So at 8k we will get our 45k point or minus 3 dB point, and after that we will get our required desired signal to go up. Second order high pass filter is same as the first order, but we are using the repeated stages. So first stage, first filter, and second stage again first filter, but with some different values, say C2 and R2. The FC, the cutoff frequency, the corner frequency, or the which frequency? The breakpoint frequency is 1 over 2 pi under root R1 C1 R2 C2. Why we are taking under root? Because if we multiply R with R and C with C, they go R square and C square. So we must have an under root with it. So now it is R1 C1 R1 C1 and R2 C2. So this is what happened. That's why this under root came into being. Okay, so this is the high pass filter. Let's discuss the use of this high pass filter. High pass filter allows high frequencies. So if we have a square wave like this and we give it to a high pass filter, it will only allow this first peak and then allow its second peak. So for first peak it will go up and then end up, and for the down peak it will go down and then this. So this is something like the shimmer's trigger. Shimmer trigger triggers a circuit with a pulse. So if we, let's say, use some diode with it, it will become like this, just like that pulse which we give to the heart patients if we want to stabilize their heartbeat, or if we use same we can also use it in the same MRI instruments or the graphing instrument, the ECG instruments, cardiographic instruments. So this structure with a little modification, a high pass filter, a capacitor, and the voltage taken from resistance is taken with a pulse given for such thing. So this pulse has benefits. This gives high energy at a very lower time. So high energy at lower times gives us what? A jerk in some scenario. So if we want to increase this jerk, now if we want to increase this, we want to give more energy. What will we use? We will take the output from this point. So at this point this will be something like this. So some of the frequencies are removed, some are not removed. So this is it for the high pass filter, that we can use it for cutting this second edge or reducing this second edge. Now band pass filter, as the name suggests, it is allowing a band of frequency. Say 2 points, one will be start allowing the band. There are 2 points, one will start allowing the band and other will delete the band. Band pass filter can be used to isolate or filter certain frequency that lies within a particular band or range of frequency. So we are having two, let's say, bands here. This one is rejected, this one is rejected, and this one is pass band. So a band pass must be of this sequence. First, it should be having a high pass filter. Why? Because we want this thing to be passed. So if we have a high pass filter and we have, let's say, this band, what will happen? This, let's say, this thing would be passed by this filter. After that, we will introduce a low pass filter with it. So what will the low pass filter do? The low pass filter will delete the higher band that is not required. So let's say this is a low pass filter and this band is deleted, this is not required, only we are remained with this band now. So first we had removed this one. Let me mark it with some different color. So first we removed this one and allowed this whole high pass, and then we removed this one. So this should be the sequence, that first you should have a high pass filter and then you should have a low pass. So this is a high pass. At high frequency it will start allowing voltages, and this will start working at low frequencies. So once the high pass is done, then this low pass comes into action and removes this band. So this band, this band. So this band was removed first and this band was removed second. This is removed because it is a high pass filter. So high pass and then low pass, and this is our required band. So this is what happened in this circuit. It can have such broader range, or it can have a short range of passing. In such cases it will be a very high tuned filter and can be narrow or wide band. So this is a wide band filter, this is a narrow band filter. Frequency response of band pass filter is discussed earlier, that it allows certain frequencies starting from lower frequency and ranging from a higher frequency in a pass band. So we are using two circuits, the high pass filter and low pass filter. So this is FL, and this FL was actually taken by the high pass filters FC. This is FH, the higher frequency. This is low pass filters FC. So we have two passing and cutting of frequencies, and both will be 20 dB because they are not occurring on the same point, they are occurring at different point. High pass filter starts from 90 degree and comes to 0, and low pass filter starts from 0 and goes to minus 90. So the phase is from plus 90 to minus 90, whereas the magnitude is from FL to FH. FL minus FH, FH minus FL, or FL minus FH is termed as the bandwidth of the filter. So high bandwidth would require this FH to be higher and FL to be lower, and we can decide about this bandwidth from the RC circuit that we are combining. So if you know low pass and high pass, then band pass is designed by combining a high pass filter with a low pass filter, and this is V in and this is V out. High pass is first, low pass is second. This is an important thing, please remember this thing. Okay, let's solve an example on this. A second order band pass filter is to be constructed using RC component that will only allow a range of frequencies to pass through 1K Hertz frequencies. So sorry. So this is the 1 kHz frequencies and below 30 kHz frequency. So this is actually a system that is allowing some, let's say, audible range from 1K to 30K is around 20K, and that 20K is an elevated audible range if you just elevate it for some encryption or for better performance. Okay, assuming that both the resistances are 10K, calculate the value of capacitances. So this is a reverse problem. We have frequencies and we want to calculate capacitances. So Fc is equal to 1 over 2 pi Rc, and this C needs to be calculated. So R is constant. First put Fc here and make this thing here 1 over 2 pi F and R. So put this thing as 1K and then put this thing as 30K to get our C1 and C2. So after this we got this 15.9 nanofarad capacitance as C1. This was the high pass stage 1 capacitance. Now for stage 2 we calculate the low pass capacitance. So low pass capacitance is calculated by the same formula, and this formula states that C is equal to 1 over 2 pi Fh and R. R is same, Fh is 30K now. So 30K will be introduced here, and this turns out to be 530. So the whole design of capacitor is that we are having 10K here, 10K here, and a high pass filter is here, so 15 is here, low pass filter is here, so 560p is here. So this is the circuit that we intended to design. Central frequency of second order band pass filter is very much important, because at this is the frequency at which the circuit is tuned. You can pass a signal on this point with a very better performance. So this will not be attenuated. So central frequency is actually the geometric mean. Geometric mean between two number is calculated as this: m is equal to n1 and 2 under the root. So geometric mean is FL into FH under the root. So geometric mean of that previous filter would be 5.48 kilohertz. This is point, not comma. So this is the circuit and this is the geometric mean for that. Low frequency is minus 30 dB cutoff point and high frequency is plus 30 dB cutoff point. So do remember this. We sometimes introduce stage buffering before going to the low pass filter. So we first do the high pass filter. We first introduce high pass filter, and then we amplify this thing. We make this thing bigger, and after that we pass it through a low pass filter. So this is a bit more we say getting more gain due to this isolation buffer, and this is used because sometimes the effect of this circuit might cause some disturbance in this. So we have separated these two circuits by introducing this gain buffer. So far we have studied low pass, high pass and band pass filter. The next topic is the band stop filter. So band stop filter is sort of inverse band pass filter, and its central frequency is same as that of the band pass filter. It is a geometric mean of FL and FH. So no doubt that these two filters will have FH and FL calculated in the same manner. Okay, the band stop filter is formed by combining low pass and high pass in parallel. In that case we had cascaded it. So this was a high pass, this was a low pass, and this was our band pass filter. So band stop filter would be a high pass, a low pass, and then combine it for the signal input. So this is stated in here. The name indicates that it will stop a particular frequency. Since it eliminates frequency, so it will be also known as the elimination filter or rejection filter or notch filter. As we previously discussed, that notch is something like this thing. Notch is the cut in the fabrics that the people do when they stretch the clothes. Okay, in practical, due to the capacitance switching mechanism in high pass and low pass, the output characteristic might not be same as these steep lines, but rather would be something like this. So it will not be ideal filter. The electrical design is either that way, or we can also write it like this. We can draw it like this, that we are having resistance in series with inductance and capacitance. And what will this inductance do? At low frequency, this inductance would have XL equal to 0, but this capacitance will make this thing open, so the signal will appear here. At some intermediate frequency, this capacitor will become short as well, so this will ground the signal for that intermediate frequency. And at higher frequency, this will become short, but this will become open, so again the voltage will go through this. So the voltage was going, and then it was grounded in intermediate, and then like this. So this makes this thing the band rejection filter. Its system response or V out can be calculated as V in multiplied by the resistance, the impedance in this and this, so we will call it ZT dash, divided by R plus ZT dash. That will be equal to our V out. So ZT dash is XL minus XC, so XL minus 1 over omega L minus 1 over omega C, divided by R plus this thing. So this gives us the formula for the output voltage at any frequency. You just put the frequency in it, and it will give you the output in terms of that frequency. So this was a bit about the electrical design of the band rejection filter. I hope you people have gotten some idea about the filter design and its mechanism of working. If you people want to learn more about it, I have put some links in it. It has a low pass, high pass, band pass and band stop filters with passive filters background. So there is no active filter on these links. You just go to these links and you can find the classwork, etc., the timetables, or the weekly distribution, the CLO distribution, PLO distribution on our official site. Also, I would want to write the link of, but let's not write that. We are having a slide share account. You can go to this site, and from here it will guide you to our slide share account. So you can also go to your slide share account and search for these lectures as well. This lecture will be having the same topic, passive electrical filters. So you can go to it and just check it. Okay, this is it for today. Thanks for watching this whole tutorial and video. Thanks a lot.